இன்னைக்கு யாருமே வரல. ஆனாலும் கூட நான் இது ரெக்கார்ட் பண்ணி போடுறேன், அதுக்காக இது இருந்தாதான். Wait for a couple of more minutes. Huh? So Naveen, you had, you're Naveen? Yeah, okay. You had logic course, huh? So did they cover resolution, DPLL, and so on there? Resolution principle? When you took it? Who did you take it under? Praveen? He did not cover proof theory of propositional logic using resolution principle and so on. So you haven't heard of resolution, okay? I guess the rest of you would not have. Or you have? You have not. How about you? Not at least these days. What does that mean? Huh? These things means? Oh, whatever you said. Okay. But you have had a logic course? Where? So you are BSc third year, is it? Data sciences. Yeah, but data sciences, logic is not a requirement, so, but you still had it, huh? Oh, okay, okay. Yeah, but BSc math, logic is a requirement, is it? Yeah, huh? Oh, okay. Who taught it? Oh, I see. Oh, it's not at CMI. Oh, okay, okay. Okay, I think I'll start. Okay. Anyway, it's getting recorded. Okay, just to set the context. So what are we? Okay. Yeah, so we kind of quickly went through DPLLT, okay, very quickly. And the reason that I wanted to do that was because, you know, I mean, I wanted to give this interaction with this LP solver and so on. But now we will kind of take a step back. You know, for DPLLT, first you have to cover DPLL, okay, which is the kind of the standard or the core algorithm that is used for deciding Boolean satisfiability. That is, it's a decision procedure for deciding propositional formulas, not with theory. And that is extended to deal with, interact with theories. And that's when it becomes DPLLT. And we saw one naive version of that without actually going into how exactly the present day modern SAT solvers actually work. And therefore now that's what we are going to get into. First DPLL, and then I'll revisit DPLLT. And those are the two things that I will cover, okay, that I want you to learn. And other than, there are various theory solvers. If I were doing a software verification course, I would cover more theory solvers that decide formulas from various theories that are relevant for software verification, for C program verification, like arrays, bit vectors, and so on. We've kind of covered the UEF thing because that is important to do this core solver, which kind of integrates these things. And I might cover that as well. But that is all that I will cover as far as the theory part is concerned. What I will do is I will kind of make a list of all the theory that I have covered so far. Besides, there are two kinds of topics that I've covered so far that we have covered in it. One is kind of SMT core, kind of the looking at the internals of the thing. That's what I call as theory, okay, and the logic, and various things related to neural networks. There I include all the modeling part of it, and how do you properties, etc. Those things are the applied part of it, which your assignments as well as you will get to know about that, and the tools the tools that support those techniques through your project. So what I want you to, just to keep you honest, in the final quiz or program, it is the theory part of it that I will cover. Okay, that's the syllabus for the theory, and I will make a list of those topics so that it'll help you to get prepared for the thing and what you can expect. Okay, so that is yeah. So the SAT decision problem for propositional logic. Okay, so it is satisfiability. Produce given a formula. Okay, quantifier-free formula that only now has propositions from the proposition formula. It does not have any theory symbols, just to produce an assignment to the proposition, all the variables in that, which are proposition variables, such that alpha satisfies F. The unsatisfiability, when you say that is no such things exist. The validity is kind of dual of unsatisfiability. You can do validity by checking. So these are some typical formulas where all the variables here, range over Booleans. Yeah. So this is a very classic. It's NP complete. Okay, and one of the earliest problems to have shown to be NP complete, and therefore all this is typically used to show NP hardness or NP completeness of various other algorithmic problems by reducing those problems into a SAT problem. Okay, so okay, these things I'm going to skip because you've already seen the various normal forms, and the one that is relevant for us will be CNF. Okay, so this thing you've seen. So let's look at satisfiability. Okay, so there are some very easy cases. Okay, if the normal forms are very important, depending upon what form you have your Boolean propositional formula in, some subset of these satisfiability problems becomes quite easy to solve. By easy, I mean more efficient. You mean either linear or quadratic, okay, as opposed to being exponential or worse than that. Okay, NP hard means it is exponential. Okay, so for example, if you have it in DNF form, okay, where you express your formula as cubes, disjunction of cubes. A cube is a conjunction of literals, where a literal is a variable or its negation. So, for example, if you have, then your SAT is very easy, okay? Because each cube is satisfiable only if every literal has to be satisfiable. Your assignment should be such that every literal is satisfiable. So, and you can always satisfy these things unless you have a contradiction in a particular variable of that kind. Okay. So, and if any one of them, yeah, so it reduced to one of checking if there is contradiction in any of the literals in any of the cubes in the formula, that which could be done efficiently by just searching. So if you had it in DNF, it is quite efficient. Okay. Did you any questions there? So did you get it? You look a bit perplexed. Yeah. Yes. Okay. So every cube, when see, a cube is a conjunction of literals. You can always satisfy them. So for example, here, by making an assignment for any one of these. Now, in order for this to be satisfiable, since it's a disjunction of these cubes, how can you make this formula satisfied? Any one of these has to be satisfiable. So for a cube to be satisfiable, the only way it cannot be satisfiable is when you have this kind of a contradiction. Okay, so if you have a literal in there, so in DNF form, each of these has to be literal, you see. It is not, you can't have any complex formulas there. I mean, it's just a two-level formula. Therefore, you could just check each cube, maybe one from one end to the other end, and then see if it has a contradiction of this kind between the literal. And since each of them is finite, you can do it in linear time in the proportion to the number of cubes in your, and the size of the formula. Okay, the size of the formula includes the number of min terms in it, and of course the variables. Okay, that's what I mean when I say, now it's clear, no? Okay, so yeah, now if you have it in CNF, validity is quite easy. Well, I mean, here, if you want to check validity in this form, validity means it has to be true for all possible assignments. Then it becomes, harder. You will have to look at all possible ways, that all of them will have, I mean, yeah, you will have to do some enumeration over all the things, and that's when it gets harder. Similarly, here, the dual of it, okay? So if you have it in a CNF formula, the validity problem is easy, but the satisfiability problem becomes hard, to see that. So a CNF formula is a conjunction of clauses, where a clause is a disjunction of literals, okay? A clause is always satisfiable. So in order for this to be satisfiable, a formula in CNF, since it's a conjunction of clauses, every clause has to be satisfiable, correct? So only then it is true only for every clause in that conjunction is satisfiable. And a clause is always satisfiable, okay? So you can always give some assignment into the thing, to it, okay? Therefore, I mean, I'm sorry, validity, not, I don't mean validity, okay? So I take it back, okay, I made a mistake. So checking validity means it is valid if all of them, I mean, every clause has to be, true for every, so every clause is always, so if it is, if a clause is valid in the sense for all possible, I take it back. I mean, what I said was wrong. So if each of the clause is valid, and that means that it is true for all possible assignments to the literals, then the whole thing will be valid. Okay. Now, a clause can be, valid only if it is of this kind. Okay. So if there is a tautology as part of it, A or A not, because if it doesn't, then you can always pick some assignment that makes it makes this clause not true for some assignment. Okay, so that's why in order to check the validity, you have to check that each clause is valid, and checking the validity of a clause amounts to checking if it has a tautology on some literal in it. Okay, yeah. Why is this not valid? Yeah, because I can pick A to be 1 and C to be 0. Okay. So then for that assignment, this won't be valid. So A, yeah, if I pick A to be 1, this will be 0, C to be 0, this will be 0. Okay. This will be true, but this will not be. That's why, this one is, so that is easy. Whereas checking satisfiability will be hard. You will have to check if there are, in order to check satisfiability, of course, every clause can individually be always satisfied by picking some assignments, appropriate assignments to the literals. But the assignment that makes a particular clause true could be conflicting with the other one. That's why you will have to check if your assignment to that makes one clause true is it's consistent with the other one every pairwise. Okay, for all pairs. So you can imagine. Okay, unless you have very clever, in some cases you may be able to do, you end up having to look at all possible subsets of these things, and that's where the explosion comes. Yeah. Okay, so yeah, so it's NP. Yes, so the satisfiability problem is defined as given any propositional formula, not necessarily in a particular form. Okay, and then any one of those. Satisfiability means not just satisfiability, doing both satisfiability and unsatisfiability, and that's why this thing is hard. And there are lots of other easy cases as well, and we will see, and I will probably give that as an assignment. Okay, so for example, if when it's in CNF form, okay, so I'll get to that. Let's see. So there are various other easy instances as well. Okay, and as we go along, I'll point out. Yeah. Correct. It'll be exponential. Yeah. And there are, okay, the reason I call it NP complete and NP hard is because so far they know that cases where it is even the minimal, this thing is exponential. Okay. So one thing to note is all modern SAT solvers, almost all, okay, they always work with CNF. Okay. Because the core engine always assumes that the formula that is inputted, the core engine assumes that it expects the formula in CNF. Of course, then there will be the question, won't there be exponential blow-up? Because when since you're interested in deciding the satisfiability of an arbitrary proposition formula, which may not be in the CNF form, and you could imagine that if you don't have it in CNF, any other which uses other thing, you can always convert them into CNF by using distributivity laws of and, or, and then De Morgan laws of negation by pushing the negation inside and so on. But that each application of that will cause each time there will be 2 times thing, and then there can be explosion of when you convert into a CNF formula itself. So even at the input itself, if there's an explosion, how do SAT solvers? A legitimate question to ask is, if all SAT solvers do, either they have to yes, I mean, if the core engine always goes in CNF, how does it avoid the input exponential size explosion. Okay, there is some clever encoding that you can actually use, which we will see later on. Okay, maybe towards the end of this lecture, or if time permitting, or in the next lecture, as to what is that, how does it avoid the explosion in the number of clauses. What it does, it's a very clever encoding, where for introducing new variables, new additional variables which are linear in the size of the formula, it avoids the exponential explosion of the number of clauses that are needed. And we'll see that. For now, this I'm going to skip right now. These are the encoding slides that I have, and I'm going to skip right now. Okay, so did I have some comment there that I skipped? No. Okay, so let's see. So I've already indicated that there are some examples here to see why SAT is hard. And I've already told you that in the worst case, you will have to look at all subsets of the clauses, all subsets of clauses. Now, is this SAT? So now we're assuming that from now on we'll have our formula in CNF form, and we are dealing with satisfiability. Okay, this is satisfiable, is it? See, that's another easy case. Okay, first is satisfiable. See, the reason you see that this one is a case where each clause has one literal, the single polarity, which appears in single polarity, okay, throughout the formula. So therefore, you can always pick, for example, E appears only with one polarity everywhere in the formula, and that appears in the clause. Similarly, F bar, and so is A. So I can independently assign them, and they're not. So the problem variables are the ones which appear with a differing polarity in two different clauses. That's the source of conflict. Okay, that's an easy case. Okay, if indeed, first you could check if there is, go through all the thing and then see if there is one thing which occurs with unique polarity in the whole thing. But in all these cases, it'll be hard. Okay, it could potentially be hard. Okay, and that's because, how do you? You might end up having to look at all possible pairs of subsets of clauses, and that is the thing. Okay, I'm not going to go into any proof of why this is NP hard, because there's plenty literature if indeed you want to go. There is one other instance, easy instance. Okay, it's called the 2SAT. If every clause in the formula, in a CNF formula, has at most 2 literals, then that's called a 2SAT problem. If every clause had at most 2 literals, okay, the variables could be as many as you want, but each clause has 2 literals, then it is polynomial. There's a polynomial algorithm, and do Wikipedia and you will see it can be reduced. Satisfiability of such a CNF formula, 2SAT, can be reduced to checking a path in certain graphs, okay? A graphical representation of the formula, which itself is known to be efficient. So where it becomes NP is starting with 3SAT, when your formulas, when each clause have 3 or more, okay, literals, and there they usually reduce it to something called a 3-clique problem of graph, okay, which is known to be NP hard, and then you can do this, okay. So so how do then Yeah, so this is kind of the intuition. It's not a formal proof that, there are instances where the minimum, that you need to, you will have to look at all possible subsets of things, and that's where it comes from. So modern SAT solvers, how do they then manage? Obviously, you can always stump any modern SAT solvers because the worst case complexity is exponential. Even there are very small sized problems, okay, for which, by small, I mean where, like the pigeonhole problem. Okay, that's the classic thing. By the way, I forgot to mention. So this reference material for this, for both today's lecture and the next lecture is chapter 2, I think, of that decision procedure book, and I pretty much follow that, and you can use that as supplement material or a reference material for for that. And I cover only a subset of that material. Whatever I've covered in the class is what, for your enjoyment, you could study more, and I can even upload certain papers and so on. But for pedagogic reasons, for the benefit of what I will be checking, what I'll be testing you on the final exam, what I'm saying is use the slides and as the reference material as you feel fit, because the SAT solving, even today, there's a lot of research that's going on, and there are conferences that are exclusively devoted to SAT and SMT solvers, okay? So there's a lot of open problems still in this area, both engineering and theoretical. Okay, so it uses. So why do modern SAT solvers, they work for huge, okay, like formulas that have close to a few millions of variables and in even small millions of clauses and so on. Why do no, that's okay. Okay. Yeah, that's because these are the three things that that is at the core. Yeah. Okay. So they, in addition to this DPLL, you keep hearing DPLL because DPLL is an algorithm that was invented like in the 60s. Okay. So at the core, all SAT solvers use only DPLL, which itself is based on this principle of resolution. So that's why it is important that you kind of understand resolution, what resolution is, and DPLL. What they add to that, in all these years, that has not changed at all. What they do, and what gave modern day SAT solvers, starting from around 2000, okay, in the last 20 years, is when there has been several breakthroughs that have kind of orders of magnitude, several, been able to, SAT solvers, due to those breakthroughs, they've been able to handle formulas of sizes that are orders of magnitude bigger, larger than what any tool was able to do until 1990s. And that is, and these are some three main things, okay? There's a learning, not machine learning like thing, okay? Some logic-based learning that it uses, okay? In order to kind of optimize the search for these satisfying assignments. That is one, okay? And the other one is lots of heuristics, okay? You will see that if you want one way, and that is DPLL is basically like that, you will see soon. How would you decide? Okay, one easy way of deciding satisfiability of a Boolean formula, if you were to do it, not giving too much, not being too clever, how would you do it? That is being smart, okay? Suppose you don't even want to do that. And that's what resolution does, okay? Yes. I suppose you have no restriction on it being the most efficient, okay? You can be as inefficient as you can. There's always that, huh? Yeah, truth table. For any formula, you put the truth table, but what will be the size of the truth table? 2 to the n. You will have to enumerate all of them, okay? Now, you could do a little bit more than that. You could kind of not do lazily enumerate, okay? If you eagerly enumerate, you will have to do 2 to the n, okay? Maybe you could lazily pick one variable, put it one thing, and maybe the formula immediately reduces to either true or false. Okay, so you see, you could do this lazily. Okay, so that is what the thing is. But even in that case, the order in which you you pick the variable to decide, etc., really matters. And so and that is one of the heuristics. Okay, so there are lots of heuristics that have been developed to to do it lazily by heuristics to decide which variable you pick. That is one. The other thing is a lot of engineering. Okay, in how you engineer the thing. Those things have made a big difference. And what we're going to see is this learning technique and this one decision heuristic that most SAT solvers use, and one engineering, patented engineering implementation technique that has resulted in giving this boost to SAT solvers for the purpose of just learning. That is what you do. So first, I'll ask the question. So that is the introduction to resolution. First, is there, you can ask is if there's an easy way to check the circular inconsistency. Okay, so because there's inconsistency, you might have to, it is circular. So because you will have to look at all the clauses and see, there could be any subset of those clauses that can be where the inconsistency can occur. So without enumerating 2 to the n truth values, of course you can enumerate the 2 to the n. Then if all the cases are false, that is that is the thing, without doing it. And that is what this resolution principle is about. Okay, this was okay. The thing is not visible. This was invented in 1960 by a guy called a logician called J. Robinson, John or Jack. I don't remember. So the idea is this is one inference rule. Okay, that's it. Yeah, and there are atomic instances of this. So given any two, so your formula now is in CNF. Okay. So and as usual, you will have to read. If you have this two clauses of this form, okay, in your formula, where the two clause has one literal with opposing polarity, which means they're potentially could be potentially conflicting. Okay. Yeah, they could be resulting in potential conflict along with other clauses. Then what it says is you could not replace, but you could then you resolve that into this. Okay, so you eliminate those two things, and then you take the union of all the other literals. This is called the resolvent. This is the original two clauses which are being resolved, and this variable C, which appears in opposing polarity, on which it eliminates the reference. So that is called the pivot variable. Okay, so those are the terminology that is that's used. So yes, yeah, that's right. So yes, we assume that it is CNF form. Yeah. Yeah, and then that's why I put the thing, this rule is applicable when either of them, okay, when at least one of them is not unit. By unit, I mean a clause with only a single literal is called a unit clause. So for the case where both of them are unit, you can have two rules. One is if you have A and not A, then it is a contradiction. So that such a formula cannot be satisfied. So that is kind of the simplest case of discovering a contradiction, inconsistency. So that is also there. And then no, this should be or. Okay, if you have A or A bar, A or, okay, not and. Yeah. Yeah, this is because a comma here is and, because that's a clause. So it should be A or. Okay. So then you could kind of simplify. It's just a simplification. So now let's look at this inference rule. So you can kind of get the idea of what Robinson was thinking about. Okay, you said somehow every time you apply this rule, you are eliminating one potential source of inconsistency because that opposing polarity is being eliminated here. So if you notice that this application of this, the resolvent is always equisat with C1 and C2. That is, since what equisat means is whenever the conjunction of the original clause is satisfiable, so is R and vice versa. Okay. And if this itself is unsat, so is R, the resolvent, and vice versa. Okay. Why? See, if this is satisfiable, what? Yeah. What can be a satisfying instance? If I pick one way of satisfying it is if I pick 1 for C, then of course this will be 0. So I'll have to then make one of these literals 1. Okay. Or or I could, I could pick this as well as one of that and one of the A's and one of the B's to be 1, in which case it really doesn't matter. But even in that case, there is always a way to satisfy one of them. So if I pick C to be 0, then the other literals other than the C will have to be a 1 in the other clause. Correct? Yeah. Okay. So if that is the case, then because in either case, in order to make this satisfied, one of the A's or B or both, okay, have to be a 1. If that is the case, then this can also be satisfied, right? Because those A's and B's are all here in this clause. And now, if this is for the reverse, if this is satisfiable, now, I can always pick C, okay, because I know this is satisfiable only if one of either an A or a B is assigned 1. In that case, I will correspondingly pick the other C, assign an appropriate value for C to make the other one, the other clause to be be true. I'll pick the C, and that's why it is. And if it is unsat, you can see this is the only case when it can be unsat. Okay, if there are only 2 clauses, pretty much this has to be. This is how it can be unsat. Okay, it's only when you have more than 2 clauses then the circular inconsistency comes. Okay, so the situation for the thing now. This is not equivalent. Okay. So the resolvent is equisat with this. So if it is satisfiable, then what you can do is you can add the resolvent to your original set of formulas. Every resolvent can be added to the original set of formula. Why? Because whenever this is also satisfied and vice versa. Therefore, adding that to the original clause does not change the satisfiability status of the original formula. Okay, but this one has one important property that it has one fewer inconsistency. Okay, potential inconsistency, and the reason it is equisat, and you'll see that implication this way holds good. Okay, C1 and C2 implies R. Okay, but the implication other way does not hold good. If R, that's why it's not equivalent. You see that these two don't have the same set of variables. Okay, this has one fewer variable, right? Because the C and C bar has been eliminated from this. Therefore, I can make this thing to be true by picking one of the B, and then this can be made to be true. C doesn't matter. Okay. Whereas C matters here, okay? The assignment to C matters here, and that's why implication this way does not hold good. So a resolvent is always implied by the original pair of clauses on which resolution is implied. And because it's equisat, I can keep adding the thing. So that is with that, what is the DP in the DPLL stands for Davis and Putnam, who were the yeah, use this rule to come up with a strategy. Okay, Robinson just proposed this resolution. He was not interested in automating this into a decision procedure. So Davis and Putnam, they were the people who took resolution principle and then did it. Of course, before that, there were lots and lots of logicians had studied a lot of logical inference systems. They were only interested in a philosophical sense, not from a computation point of view. And that's, you know, so these were the, at least based on the resolution principle, these were the first one to discover some automated decision procedure. And you know, pretty much this is what you do. So what they say is Davis Putnam is that, and what does that do? So given a CNF formula, you repeatedly apply resolution, okay, until you keep on applying, until you either derive contradiction, in which, or pretty soon you will not be able to apply. You will not be creating any new resolver. So this resolution inference rule will not get, you know, you will exhaust the thing. Then you do that, okay? And if then phi, the original formula is unsat, if you're able to derive a bottom through a single inference rule, okay? That's why it is so attractive. And otherwise you declare to be it to be sat, okay? So when you end up without, you know, without no new resolvents being produced, you'll end up with some set of original formula and all the new resolvents, and that will be a satisfiable thing. And sometimes you can end up in the process of reducing the original formula through resolution to true, okay? That's also a possibility, okay? You can simplify to be true. Now, yeah, so that is DP. And until, like I said, 1990s, mid-1990s, that is what was being used. And it was, you were not able to scale such a thing for maybe a few hundred variables, okay, nothing beyond, you know, beyond that. But there were systems that were, you know, used. So let's see the application of resolution thing. So once again, the three formulas that I've shown here. Okay, so that's visible, I hope. Yeah. Good, you can move on. Yeah, okay. So let's take, I think it's this one. Yeah. So each time here, I'm resolving on the variable b, these two clauses. That will eliminate b and b bar, and it's a in both things, so it will come to a. Similarly, I can take these, do a resolution on this thing, on c, the variable c, to get a bar. So, and then a and a bar will give rise to bottom. Okay, so therefore it is thing. Similarly, it's the same thing. Okay, it's the same formula. You know, I'm just illustrating, so there is no unique, you know, resolution graph. This is what is called a resolution proof. A proof is an artifact of showing the original thing is either sat or unsat. And this is a representation of a proof. And there's no unique thing because it all depends on which variable that you choose to pivot on and which clauses that you do. And some proofs can be very small, very compact. The others can be everything. And that's kind of what boils down to choosing which variable to pivot on and on which clauses is very much like which variable you decide on, okay, when you, for any automatic procedure, okay? So similarly, what would happen in this case? Okay, this you said was satisfiable, right? What would happen in this case if you were to apply? Let's see, okay? So what can you do? So you could resolve on C, because that's the only variable, you know, in these two things. So that will give rise to a resolvent, A or B or not of F, okay? Huh? Well, but you still, in order to check the no more resolvent produced, you still have to check the thing. Okay, so you could do that thing too. So let's complete this. Okay, C bar, and then you get this, and then you will do B and B bar, and then F bar and E. Okay, see yeah, you'll have A, F bar, and E. Okay, see those, it'll be left with, so two things to notice. One is that you can't, in this case, you had to see, in this case, all the new resolution were only on new resolvents, the resolvents that were produced, not in the original formula. But in this case, after doing this, you had to resolve with the resolvent could be resolved with the original formula. So which means in this Davis-Putnam strategy, you'll have to keep not only the original formula, but potentially all the resolvents, okay? Because how else can you check that there are no new resolvents? Now, so there is, when you say there's no new resolvents, it could be between newly generated resolvents as well as between newly generated resolvents and your original clauses. You will have to check them as well, like you did. So anyway, in this case, what happened was after that, no more resolutions are possible. And what you end up, the resolvent that you end up finally will contain A, F bar, and E, which are exactly those literals and which you could assign whatever way you want, and you could get a satisfying assignment. Because for all the other things, you have to choose appropriately everything. So, and that's why. So if you so there is a way to extract, although it doesn't directly say it, there's a way to extract your model, okay, by looking at the resolution graph as well. Yeah. Yeah, but that is no, but it'll certainly be one of the resolvents. Okay, that'll certainly be one of the resolvents eventually, but you may not get one resolvent in which all of them might be there. Okay, they might be there as in different resolvents. Okay, so in this case, it so happened all of them happen to be in the same things. There's no guarantee that you will have it in the same resolvents, in one resolvent that will contain all of them, but it'll be in some resolvent. It'll park in some resolvent that is that is there. Okay, so that is one related. So the resolution graph, that concept, resolution principle, and this is what is sometimes called resolution proof. Okay, so nothing is just what led to your either contradiction or showing that it is SAT. Yeah. Okay, now there is this notion of unsat course. Now you can go into Z3, and then it actually gives you what are called unsat course, and they're very useful. Although they have a very formal logic definition, in practice, in engineering practice, they give you a lot. They actually tell you. I mean, I'll define. Okay, now as you saw, this one was unsatisfiable, correct? When it is satisfiable, what you want is what is the model. Okay, that is what is of interest. When something is unsatisfiable, so this one is actually a unsatisfiability proof of this formula. Okay, and see, there is one way to derive a bottom from these set of clauses, which I have put within square brackets here. Okay, and there's also a way to do from this, from here to this clause, and these clause also end up, no. In this case, this is the only one. Okay, so this one will not yield a thing. But Yeah, so in this case, all this set of clauses, subset of the original clause, is inconsistent. Okay, since you have to have all the clauses satisfied simultaneously, in some sense, this is called an unsat core. Okay, that is the essence why this formula, that's the kind of a core reason why that formula is unsatisfiable. Okay, some subset of the original formula. Subset means subset of clauses in the original formula, which is the source of your conflict, okay, is what is called an unsat core. So that gives you kind of an essence and insight into why your original set of formulas, some minimal, insight into what is the minimal set of for clauses in the original formula that led to your unsatisfiability. And that's what an unsat core is. Unsat core of an unsatisfiable formula is a subset of clauses of the original formula that is still unsat, okay? But any smaller than that subset is satisfiable, okay? In some sense, it is, in this case, this happens to be the only thing, okay? All the rest, I think, are a thing. In some cases, you can have more than one unsat core. So here, the one within curly bracket is one unsat core. I don't know if I have, yeah, and the one between square brackets is also another subset. Okay, one is bigger than the other one. Okay, there are two subsets of clauses that are responsible for making the original formula inconsistent. Okay, and you can see in that case, if you do the resolution proof, you will get one proof of a bottom with those clauses, one that subset and the other one. So if there are multiple unsat cores, then there is this notion of a minimal unsat core is one of the smallest among those things. Okay, there could be multiple with the same size. Okay, we are here by size, I'm measuring the number of clauses. See, this is defined in a very mathematical, logical way. Okay, since we are talking about these things, formulas modeling real artifacts, okay, like programs or DNNs and so on, when you're checking unsatisfiability, okay, to show that it is something is valid, okay, something is proof, then you could say why it is indeed unsatisfiable, or maybe the unsatisfiability can be, if you model it in such a way, the unsatisfiability can explain why a bug is there in your original formula. This, searching for unsat cores can give you an explanation, for example, as to why that indeed can explain your why the original property either gets verified or or fails. Okay, so that's why getting unsat core can give you an explanation. Okay, and that's why this is quite useful, and most SAT solvers also support these things. So I think it is important for you to know these things, and if indeed you do some further research or exploration into this thing. Okay, so the drawback of Davis-Putnam. Okay, so you kind of understand the concept, no? So I didn't. I don't think we will be doing in a project anything related to this, but I think it's an important concept that you should know. And since most tools, SAT solvers, do allow you to extract this thing, yeah. If not the minimal unsat core, at least one of the unsat cores. Okay, they do allow. Okay, so as I said, the reason that this didn't scale, okay, it doesn't scale, is because it is memory intensive, need to potentially keep all of the new and the old clauses, which is not good. And then there is this issue of how you extract models when your proof does not produce a contradiction. Some cases it's easy, in some cases it may not be that easy. And the proof, the resolution graph that that you need to produce very much depends on the order of the variables that you pick and the which clauses that you pick. And there is, whereas the resolution principle does not give you any guidance. Okay, of course you could do, you could one of the things that in the early one that they used was to bias your resolution towards unit and short clauses. Okay, because if there are in your original formula, some of the clauses, a unit clause, you know how, if it's only unit, that forces a decision on that particular variable, right? So it makes sense for you to pick that variable to pivot your thing on. Okay, and that is like you have to, there is a forced decision on those variables. So it is always good to pick those variables to decide on, which in this case to do the resolution on. Similarly, you should, rather than picking a big clause, if you can bias your search of your resolution graph towards applying resolution inference rule on short clauses, that seems to do. Okay, so but what was the next thing? So that is the drawback why you could do these things. Okay, so the research DPLL was using some of these ideas to reduce the search space. It does use resolution principle, but in a very restricted way, by biasing it towards only unit clauses. Okay, doing unit resolution, where one of the clauses that you pick for doing the resolution is always unit. Okay, and if you do that, then your resolution, that gives you a guided thing, and that kind of amounts to, as you will see, picking one variable at a time in your original formula and forcing a decision, making a decision on that. Okay, and that decision may be wrong, or if you're lucky, it could be wrong, in which case it may get you a satisfying solution. Otherwise, you might have to backtrack, as you will see. Okay, so whereas the resolution, the Davis-Putnam strategy did not need any backtracking, this will backtrack. Okay, so that was this was more guided search than that's what this DPLL, this is what the resolution right now. So far what I have is just educating you about resolution, and yeah, so this is the first DPLL, and believe me that all the procedures in even present day solvers, this is what they use. Yeah. Okay, so given a set of formula, what is DPLL? It does what is called BCP. This stands for Boolean constraint propagation, okay, which is a fancy name used to say, if there is a single variable on which I decide whether it should be 1 or 0, plug that decision in all the clauses and simplify them. That's all this thing is. But since we are looking at resolution, so I told you that it is biasing towards unit resolution. So it says only use unit resolution. Okay, don't take, original Davis-Putnam strategy allowed you to do resolution between where both the clauses were non-unit, whereas here it is restricting the application of resolution principle where one of them is always a unit clause. Okay, so it could be either this fashion or P bar or P. The other one can, so if it has an opposing polarity, then you can apply the resolution principle. Then you will get all the remaining literals of this thing. Okay, that is instantiation of the original resolution principle for a unit where one of them is unit. Or if you have P, then it's as though you plug that P in here, because you have to make this P to be true for this to be true, right? So just like plugging that P. So this forces the decision for P to be true, and therefore you can plug that thing in, then this whole thing will get rise to P, or to true. And you might have situation like this, okay, where you have P and P naught, then it's a not P. Okay, so this, and that's what BCP does. What it does is it applies one of these three rules. Okay, I say till fixed point, what it means is keep applying them until you can't apply them anymore. That's what fancy till fixed point means. Yeah, like you remember, there was one other instance where we used fixed point. Can you remember? Congruence closure. Okay, so you kept propagating these congruent closures until you could not propagate it anymore. Okay, that's an instance of computing closure. Okay, that is same thing as computing fixed point. So that's all. So you keep applying this. So when you apply, when you still have some left over, I mean, not a true or a false, then it is something called unresolved. But as a result of this, this clause here could end up being a unit also, because if there is only two literals in there, then it becomes a unit, or it can remain as an unresolved clause, which has one fewer literal, okay, than this one. So that is the result of that. Or in this case, it reduces to true. So which means that particular thing is now, that clause is satisfied. Okay, that's the status of that. And or you can, as a result of these things, you may end up getting this kind of a situation where you have some conflict. Okay, and then that situation is called conflict. Okay, so that's would be the result of doing BCP. Okay, so you do BCP on your original set of formula. If it is reduces to this kind of a true, then you know it is satisfied. If it gives rise to conflict, then you know it is not satisfied. So that's what this thing is saying. So you true or false. What happens if the result of BCP does not simplify it all the way to either true or false as a result of this unit resolution? Okay, I mean, see, I call it unit resolution. You probably have guessed it. You make a decision on the variable and then you plug it in. In this case, if the original formula itself had only some of the unit clauses, then the decision is made for you. And that's what this step is doing here. But what if, as a result of plugging everything in, there is still, it does not reduce to one of these two things? Then what do you do? Okay, then what it says is you make a decision on it. Okay, this is what I call this deciding lazily. Okay, so what you were doing, you suggested, okay, you can enumerate all possible. That's not what I'm doing. I'll try to do this to see if without making any decision, if I can reduce it. Otherwise, I will reduce it to true. I mean, I will pick a variable and I will make a voluntary decision. Okay, that may be a wrong decision. Okay, but at that time I make a decision, and then I'll have to try both the P and the not P. Okay, so I'll add that to my G that I get as a result of doing this BCP, which is in this case is what I'm having, and then I'll add this what I call as forced decision P on that. Okay, and if either of those becomes true by applying this DPLL recursively, okay, then it is true. Now, if this itself gives me, then I can stop there. I don't even have to consider recursively this part. But if I don't, if either of them, then if both of them is false, then I know. Okay, then the thing, and then I'll have to do so. So this is where you will have to make a decision, and sometimes you will have to go one path with one decision, and then you have to come back. That is the backtracking, is what I'm saying, and then consider the other path for each decision that you do, and that's what this thing. So this is taken from the book. So here is that was a recursive formulation. So here is like a flow chart. Okay, so given any formula, you first try to do BCP. Okay, how can you do BCP? What's the use of doing BCP even without making a decision? I already explained, because there could be some unit clauses there, right? So this can be propagated. If that itself gives rise to a conflict, for now you ignore this analyze conflict, because this is doing something more than learning, etc. For now, assume that this does nothing. Okay, except it does nothing. There is, for this formulation, assume that this check is BL is equal to 0, and this one is BL is greater than 0. Okay. So what BL is stands for backtracking level. Okay. At the beginning, it is initialized to 0. And every time you make a decision, an explicit decision, then you will increase the level by 1. Okay. So first you do BCP, and if there is a conflict, and then if BL is equal to 0, then it is unsat. And if it is, so if it is equal to 0, and then if BCP is yields to true, you will go into a SAT. If not, then you will have to, what you'll have to do is to backtrack. Okay. And the backtrack, what it does is it checks if I have made both decisions on that variable. Okay. And every time I go to a next level backtrack, I increment the decision level. So I come here when there is when I'm at a decision, one more decision. So there I will check if I have done both, considered both the P and the not P. Okay. If so, then I will decrement the backtrack by 1 by going to the previous decision level, and then I'll have to flip. Okay. The decision if I'm not considered both of them. That's what you keep doing. So here you're considering the thing, and if at any point you end up not getting a conflict, but you end up getting this unresolved or true, then you go here, and if assigned all of them, if it's true, then you know it's SAT. Otherwise, you have to make one more decision. At this point, every time you make a new decision on a new variable, you increase the level by 1, and then you do BCP again. Okay. Yeah. What? Alpha is the assignment, the partial assignment that you have made. Every time you make a decision, explicit decision, which is what I call, on your variable, you have a partial assignment to the variables. Okay. And that, if you could either have, at the end of the day, you might end up getting all the variables are assigned, then you know that it is SAT, or you may end up a partial assignment and the rest may be reduced to true, also you reduce to 3. And then if not, then by the time you do all these things, you would have tried all possible things. Okay. Variable assignments, then you might end up producing it unsat. Okay. So, and this is kind of the things. So let me take another 10 minutes. Yeah. As I said, it's in decide. Okay. So every time that, as a result of BCP, you don't get a conflict, but you don't get it true either, but you have, either true or there is still some unresolved clauses, then you will have to make one more decision. You will be extending alpha one decision at a time here. Okay. But at any particular point, you may have a partial assignment. Okay. And you may get lucky, and even that partial assignment, with that partial assignment, you may reduce the whole thing to true, and then you don't need to go all the way through. Yeah. Mm-hmm. Mm-hmm. Correct. That's what, here it always says. That's why you first check at that level if you've done both. Okay. Only, if you have not, then you will only flip the decision. Okay. You will not decrement. You will not, so you will have to consider both at that. Yeah. First you will consider A is equal to 1. The next time you will consider A is equal to 0. And then if you've considered both, then you will decrement the decision and go to the previous level, earlier level, where you would have either considered 1 or 0 for the previous assignment. Yeah. And that's why. So at every level. Yeah. Then the BCP, because you would have flipped, you would flip the other decision at the previous level and then you come back. Okay. And that's the thing. So you will, yeah, so that's what is happening here. So an example would probably make it clear. But the thing is, you have to observe. So here we are not we are keeping only the original clauses. As a result of this thing, unlike the Davis-Putnam strategy, you will see that I'm not keeping all the new resolvents here, because as a result of this BCP, the status of these things will change to either true or become false or unresolved. Okay, so it is, if anything, an original set of clauses with some simplification on it. So I don't need to keep any new resolvents, and that's why this is more efficient. But the price you're paying is sometimes you will have to make explicit decisions, which may be a wrong decision for which there's no solution, in which case you will have to backtrack. Okay, that backtracking will is the price, the overhead that you're paying. And all you will see very soon, next class, we'll see that is one significant breakthrough that really catapulted SAT to the thing, and it's called CDCL, conflict-driven causal learning, which really reduced the number of backtracking that you needed to do. Okay, so here is what this thing. With this, I will stop. Okay, this is the original set of clauses that you have. So, and this, as I do BCP and then make decisions, you know, there is something that there is a decision tree that I'll have to maintain, because in order to backtrack, etc., I do need that thing. So in the beginning, see, there's a solid arrow here, means I've made a positive decision on it. Okay, that I'm setting this to be decided to make X1 is equal to 1. So in this case, if you apply BCP, there's nothing that happens here because there's no unit clauses here, correct? So everything remains as is, or I'll have to make a decision. So I choose to make a decision of 1 on it. As a result of that, X1 is 1. Therefore, these two things will reduce to this. Then, of course, it's still unresolved. So I make a decision X8. I mean, what? In the beginning, as you can see, it was just a BCP. So you did not. So if you did BCP, what will happen? If you did BCP, since there's no unit clause in this, nothing gets propagated. And it's, you know, so therefore you will go, you know, go on the left side, and then you will have to first. Yeah, and yes, you have a choice there, okay, which variable you to pick, what polarity that you make it. But here I've done that, okay. I've done this one. So your entire search will depend on these decisions. That's why the heuristics for making the decision is a very important component of how efficient your thing is. This is somewhat similar to which variable you choose to pivot on in your resolution. Yeah. Okay. So, and then once again, after X1, I'm getting this. Now it's clear, no? Okay. Therefore, still nothing. So I'll have to make a further decision. So I do X8 to be 1. So if X8 is 1, then this will simplify to this. Now X7, I'm making a 0 on it. Yeah. Now there is action, okay, in BCP. The moment I make X7 to be 0, you see what will happen. This will reduce to unit clause, okay? So the BCP kicks in when you have unit clauses, okay? So that forces the decision X0 on this. As a result of that, yeah, as a result of that, C5. No? Yeah, well, I mean, there are several possibilities. Okay, here I'm using X7 becoming a 0. Will X7 being a 0, I could even say, yeah, X6 has become 0. Similarly, X5 becomes a 0 as well. Yeah, X4, when I plug that thing in here, X4 becomes 1. and so on. Yeah, so that's what happened. After that, x4 became 1, and after that, yeah, x3 became 0, x2, and as a result of that, x2 became 1. And then when I plug these two things in here, there is a conflict. Okay, and that's what this thing gives me. So because this was due to my voluntary decision, so I'll have to change something, and therefore what it does is it goes back one level and then explores the other thing. Okay, so yeah, so I'm exploring x7 to be 1, and in this case, if I did that, it'll indeed give a thing. But of course, it once again depends on, I mean, what further decisions that you that you make. Okay, so where I want, okay, I mean, this you could follow, and what happens? Okay, this is what I want to cover and then leave it. Okay, so this is, see, in this case, just by flipping the decision x7 after backtrack, I mean, flipping the decision and making I chose to have, and as a result of which and then because these two went away, I had to make a further decision, and I happened to make a decision of 1 on x4. Okay, that led to a satisfying solution. Of course, there's no guarantee. So what I'm saying is, see, you can have this kind of a situation depending upon the decision that you make. So this was your original conflict. After that, let's suppose instead of x4 to be 1, I chose x5 to be 0. And then if x5 is 0, what will happen? So all the way through was there. Yeah, and when x5 was 1, I still have to make a decision. So then I make x4 to be 0, okay? Then I'll get the same kind of a conflict, okay? So you can end up getting these repeated conflicts, okay? And of course, it depends on the situation. So what the thing that I'm making is I'm trying to illustrate 2 points. One is your search size of your, the thing that you search for, the thing can be crucially dependent on the decisions you make on the thing. Even if you were wrong decisions, the question is, can I, here I'm not learning anything as to from this conflict, to what and why, what led to that conflict. If I could learn something from that conflict, can I avoid this thing? Okay, this kind of a repeated conflict. It turns out in this case, once you make a decision 1 on x1, x4 can never be 0. Okay, that's because this is an implied thing. Okay, so if as a result of these two things, okay, this is an implied thing. Okay, it's a true fact. Okay, the result of the original set of clause, this is something that is true. x1 and x4 can never be simultaneously the same. Okay, and since I had made a decision of x1, so I was blindly, either making x4 to be 0 or making other decisions, which in turn forced x4 through BCP to be 0. And I was running into the same conflict. Every time in the conflict, you have to backtrack and then do this thing. So that is where they observed that a lot of energy and effort was being lost. So the first thing was, if you could learn something from the conflict. In this case, what you do is, when you first time you get this conflict, you analyze that conflict, and then you learn and you add this something called a conflict clause. Okay, so which means you're pretty much somehow you have to analyze that conflict and see what the root cause of that conflict was, and then add something which could prevent that conflict in the future. Okay, when you make wrong decisions, that'll guide you into hitting into the same kind of conflict. Now, if you added this, and let's suppose that you, after you got this conflict, okay, and then when you made, where was that, x7 to be, I mean, if you had added after this, as soon as you add it, what's going to happen? You're keeping x1 to be still 1. This will immediately makes a 0, and it forces the right kind of decision on x4. So you will never be able to make x4 to be 0, which was the reason for the original conflict. Okay. That's right. So that's, you can do different things. One is having this, okay? Then the question is whether you just backtrack as before only to x7 with this new additional conflict, or you go back to x1, okay? Because there is still some solution here for you, okay? So it may prevent you. So, I mean, that is a very good question, okay? So why do you undo all these things and then go back? Because now you've learned a new clause. I will start from the one, where I made that decision. I may keep the decision, okay? Or flip the decision, whatever. Or do you still keep the clause and then only backtrack to x7? Even then it might be useful, because it may prevent you some wrong decision at this level, okay? Then maybe here there might be some solutions right there in the shallow region you might actually get. Yes, that is another thing which instead of doing this chronological backtracking, which was what we were doing, okay, only do one backtracking one level at a time until you explore all the things. Maybe you could skip levels and then try and look for a certain solution which is shallow rather than deep in the thing. So that was a second kind of optimization. So, but the first one, the point that I wanted to make was learning from this conflict and then you die. So there are lots of questions here which we will explore. Okay, so how to automate this learning of clauses, and there could be lots of reasons, the way to avoid this conflict, okay, and which one you will pick. You pick to add as a conflict clause to add, okay. And yeah, so if there are multiple ways to block this conflict, which one do you do, and so on. And then there is this non-chronological backtracking, and there is decision heuristics, okay, which variable that you decide on. So what I have just motivated you, the value of learning conflicts. In the next class, I will tell you some way of analyzing the conflict thing and then deriving the conflict clauses. And then I will go through the decision heuristic and then the value of what you Rohan, you pointed out of, whether there is value in doing non-chronological backtracking. Okay, so I will stop there. Yeah, thank you. I don't know if there are any other people there. Oh, what happened? Oh, there's no one there.